Ever since I started getting into robotics and CNC equipment, I always wondered how they could design motors and the programming behind them that would allow such incredibly precise motion. And when you think about it, if you've seen a 3D printer or a CNC machine running, they can get motion down to tenths of millimeters, sometimes hundreds of millimeters, thousands of inches. And knowing what I know about typical motors, AC and DC motors, I always wondered how that was possible. Well, recently I've been doing a lot more work with stepper motors, one of the most common types of devices, and there's small ones all the way up to large ones. And you'll find these kinds of motors running all sorts of machines, including not just the CNC traditional machining stuff, but also regular printers. If you take one of those apart, you see these stepper motors inside. So I wanted to do just a little bit of experimentation with it actually for some projects that I'm working on right now, and I ran into a few challenges, so I thought I might kind of share a little bit about some of the things that I ran into, so that if you're ever interested in doing projects like this and running some stepper motors, then maybe I can save you a little bit of some headache and learn from some of my mistakes. So let me show you a little bit of the wiring and hardware setup that I've got, then we'll look at the code that I wrote to at least run through some preliminary tests and get you started with running a couple of your own stepper motors. So first, let's look at the hardware and the wiring for this thing. Now what I'm starting with here is just a test. So all of this it looks kind of ugly right now with wires sticking out and a control panel that isn't really well formatted, but really all I wanted to do was just as easily as possible experiment with the control system, the wiring and devices, and with the coding to make sure that this was going to work before I put the time into building a professional project. So for control right now, all I have are just two joysticks. Now these are single axis joysticks, so there's two of them. And basically what I wanted to do with this was run two different motors, each with an independent axis. Now sometimes you can also find these really inexpensively. It's two axis joystick. And so it could control both of them. Now this uses analog inputs to the control system that I'm using, which is an Arduino board. I won't go into the specifics of Arduino or how that works. That's for a whole nother time or place. But we do have two what they call analog inputs coming into the board. Now over here, I have my two motors connected to two Gecko stepper driver boards. So as I move the potentiometers, you can see the motors running forward and reverse. So that's the overall architecture. Now let's take a look at the wiring a little bit more close up to see what's going on. To properly drive a stepper system, you need a few different architectures here. So the first one is the power supply. Now the main power for the motors, which actually you can feel they're getting kind of hot right now. That's just the way stepper motors are meant to run. They get a little bit warm. But the power going to those coils does not go through your control system. So that means that you need a power supply. And here I just used an industrial DIN rail mount 24 volt power supply. Now one thing with stepper motors, even though you may not have the numbers may not be printed on it, but if you can find a data sheet, it might list something like, for example, I think these ones were 1.7 amps and like 2 volts per coil. So I looked at 2 volts per coil and I thought, well, 24 volt power supply. Does 24 volts, does that work when you're only supplying 2 volts for the coils? Because normally you don't run a device with more than its rated voltage. But what happens here is the coils have a specific amount of resistance. They're just wire coils inside. Now, on the driver boards, those are limited in the amount of current that they can send. So really what you're doing is limiting the current, and when you have a constant resistance, it ends up limiting the voltage, even though the supply is much higher, 24 versus like 2, the current is what's really important. So that's what I really want you to take to come away with this. Remember that current limitation on the stepper boards. Almost every stepper driver board, whether it's switches or in this case a resistor, those are going to be able to select the amount of current. So make sure that you don't exceed the current for your motors. Now the control system side of this is an Arduino board. I used a Mega just because I need a little bit of extra memory for this project and a little bit more I/O expansion for later on. And there are 3 signals going to each of the 2 stepper driver boards. Those signals are the step and direction, individual steps to send 1 pulse, 2 pulse, 3 pulse to get it moving around, and then a direction to be able to do forward and backward. So if I move these, you notice now it's going clockwise. I move the other way and it's going counterclockwise. I need that kind of control. Now there's another one called a disable according to the data sheet. When I look at the code here in just a minute, I'll explain these all a little bit more in depth. The 2 analog inputs coming from the potentiometers, that's what you see here with the blue wires. Now, wire nuts and things like that, this washers to space things on a piece of extrusion aluminum. Obviously, this is not an official final build. This really isn't very clean at all. But it does give me a very nice stable setup that has consistent wire colors and very consistent placing so that if I need to troubleshoot issues, then I can do that. So let's take a look at the code running this thing. Now, like I said, I had a few challenges when I was designing the original program to run this, and this is only a test at this point, so I'm sure there will be a lot more improvements later on. But I just kind of wanted to give you my very first impression just so that maybe you can avoid some of the same pitfalls that I had when I was first getting started. So first of all, I used the beta version of the Arduino IDE. If you're not familiar with that, I'm not going to go through all the nuances of how that works and how to get it set up. But like I mentioned and you saw in the earlier, I am using a Mega board. This is just to allow for future expansion, and since I will be putting it in an application that is going to use quite a few data points, it's going to have a lot of memory saved into it, so I needed the extra memory size that the Mega provides. So I was setting up all of the enable, step, and direction inputs, which are necessary for the stepper motor driver to be able to do its job. Now in my documentation, I am using Gecko G251X driver boards. In the documentation, it calls one of the pins the disable. That's a little bit of a confusing term because it says when you turn it to low, at least in our Arduino language, when you ground that pin, it will force the windings to 0, which means essentially grounding it will turn off the motors. So therefore powering it turns on the motors. And to me, I feel like that's more of an enable rather than a disable. So you can see here that if I've got two motors, I left them as enable as opposed to the disable, which you would see in the documentation. The step and direction are pretty straightforward. I will need to be able to to turn on and off the steps, and I will be able to write the directions by digital writing high and low later on. Now for the setup, you saw from the little panel, I have two potentiometers, and those are serving as the speed controllers for the setup. I also put in just a couple of integers, spare integers to do some math with, and here the only one of the challenges that I ran into should have been pretty predictable, but as I'm using delay microseconds to be able to get faster speeds, some of the times, if you want to make a long pause of several milliseconds, then you're going to be running into several thousand or tens of thousands of microseconds. That pushes up against the limit of an integer, so I used a long so that I would never have to worry about having a delay that's in microseconds that exceeds the length of that long data type. All the pin modes are set to outputs, and that digital write, I turned the enables to high right here. If I needed to turn them off in my application with a robot, if I wanted to manually jog the robot and turn the motors off so that they weren't forcing torque back against me, then I would be able to write those low, maybe have a toggle switch for a hand manipulation mode or something. Now, I included a serial begin because I was doing some debugging at the beginning. Give me a couple of minutes and I'll come back to that and explain what kind of caught me off guard. But again, very predictable. It's easier to look in the past and know why something was challenging. It took me a little while to figure it out. So I turned the void loop. This is the entire loop code here, where I read the potentiometer and then drive the stepper for both the X and Y. I felt like that gave me a lot more ability to just work with one subroutine later on, rather than having to manipulate an entire code if I made a mistake in manipulating it twice. So again, if you're not familiar with subroutines, definitely recommend taking a look at those. They really can make your life a lot easier. This one, I input a motor number, so I can write motors 1, 2, 3, 4. Right now I've got 2, but I want to be able to set it up for more. And then the analog value, and then I used a long of min and max time. That's what the 5 and 5000 refer to here. Now I'll be using it as a delay in microseconds, so you can see that'll go between 5 and 5000 microseconds. Now 5000 microseconds is 5 milliseconds. Still not a really long pause, but a whole lot longer, 1,000 times longer than 5 microseconds. So I did some work here. I won't explain all of this. I just kind of wanted to give you a quick run through here. And then for motors number 1 and 2, since it's going to be running through each one of them, all I have to do is just choose either X or Y. But again, this switch case This is an easy one because if I had 3 motors, then I would just make a third case 3, and maybe I have a Z, which actually on this robot I will have a Z later on, and I can do some slightly different steps to it and have maybe some slightly different delay times. This is why I didn't make the single delay times, the 5 and 5000, set up as one set of numbers at the beginning, because I may want 2 different axes to have 2 different jog speeds. So that's why I allowed them to be set individually here. Now in these cases, I was running into some issues, so I put a couple of digital or some serial prints in to be able to see what my delays were as I was stepping through it to make sure I was doing the math correctly. And no matter what I was doing, it would pause or it would be running too slow. So even if I was pushing the joystick all the way, I could see that the delays of microseconds were correct. It should have been a very tiny delay, which means a very high speed, but I just wasn't getting that high speed till I realized that the serial prints that I was using, I was not only saying x val equals or x speed equals something like that, x time equals, and then the integer. It was taking so much time at 9600 baud rate that it was putting an artificial delay in. So I have my delay in microseconds for each one of these, one at a time, to make the steps, but it didn't matter because I was forcing a longer delay because I was using the serial prints. It's just, there's a finite amount of time that it has to take to write that time into it and send the info to the computer. So I just deleted those back out. Probably at this point I could delete or maybe just comment out the serial begin, but it doesn't really affect the code at that point. If I wanted to go back and do debugging, I'd uncomment that and maybe stick in a couple of numbers. Great for debugging your code, but just be aware that they do add times in, and when you're dealing with just a few microseconds delay, you are definitely going to have some significant time errors added in because of that. So that's the scope of the project, really. Now, all we really need to do from here is design the pretty package to put it in the project, which in my case is a little robot arm. And I will also need to design a belt drive system, much like you see on any typical CNC or 3D printer. The belt drive that allows the motion to go from the little gears that are attached on the motors to an actual joint of some kind. But really, other than that, the hard part is now done. So there will be a little bit more to this project, but that gets you started with stepper motors. And I hope you enjoy this kind of stuff as much as I do. It's a lot of fun to experiment and learn new things about in motors. They're old devices, but it's just some new techniques that we can use to maybe cannibalize some old projects, tear some things apart, and reuse those pieces for our own projects. So if you have any particular questions, just let me know in the comments. Maybe there's some cool project that you want to work on that I might be able to help with. I love experimenting with new things, so let me know if you have any questions like that. But in the meantime, go build some awesome stuff.